Hello, Physics 4DS. We have a short video here about efficiency in transformers. You should by now have watched the video that was already posted about electromagnetic induction in transformers. But one of the issues is that they didn't really differentiate between an ideal transformer and a real transformer. Efficiency is something that is a measurement of how much energy is put in compared to how much energy comes out. In the ideal transformer, as described in the other video, these ones are 100% efficient. Now, in the real world, that doesn't really happen. But when we're looking at physics, sometimes we choose to make things idealized, like when we said we didn't have to worry about air resistance in projectiles, or we could sometimes make things frictionless when we were pushing something along a surface. We sometimes idealize the situation. So for an ideal transformer that's 100% efficient, that means that the power in is equal to the power out. So if you remember our power equation from previous unit, P is equal to V times I, that means when we have the power, replacing it with voltage times current, remember the power for the input was called the primary, and the power for the output would be the secondary. So when I write the equation, I can either put power of the primary equals power of the secondary, and then I can replace my voltage and current in there. So voltage in the primary, current in the primary, voltage in the secondary, current in the secondary. So this was how in that other video they came up with the whole VP over VS equals to IS over IP. They kind of just mentioned it. They didn't really explain where it came from, but this is the derivation of that relationship. Now, you're not going to have to replicate that derivation, but it's kind of a little bit easier way to remember that relationship because you want to notice, hey, the primary voltage is on the top, but the primary current is in the bottom over here because as this one goes up, this has to go down. Now that's for things that are ideal transformers. So if you ever see that in a question, that means that we get to use the power in equals to power out. For some transformers, so if we have more like real life transformers, those are going to not be 100% efficient. They have reduced efficiency due to heat, usually. If you have ever noticed, if you've had anything that has been plugged in with a very large adapter, thing like this one's called an Adaptopack, you'll notice that this is actually a transformer. It has an input voltage of 120 volts and an output voltage of 6 volts. Now, it outputs 6 volts DC, so it also rectifies the current at the same time, and it has a maximum of 100 milliamps. But we know that there's a transformer in here because it's changing the value from the wall, 120 volts, to a value of 6 volts that we would need inside. But if you've ever plugged in anything, this one's not for your phone, obviously, because it has a different jack on the end there, but you especially notice it when you plug in your phone. You take that out of the wall, you hold on to it, oh, it's very warm. So that's the real life transformer because it has reduced efficiency due to heat loss. So that means while current is flowing through the transformer, some of the electrons are influencing other materials around them and causing them to heat up, to move, to have a little bit more motion and therefore kinetic energy. You can see on anything, now you can go home and check on your Well, actually, you're all at home. Wait a minute. You can go and check on your device to see what that transformer has. Even the little white cube, it has a value typed on it. 120 volt input, positive 12 volts. This is an HP adapter. So it has a transformer inside there that's going to convert whatever's coming from the wall into something usable by your device. Okay, so check that out for your device right now. Now, well, I'd like to talk about how we calculate the efficiency of that device. So if I ask you for the efficiency of what you have, you're going to take the power out and then divide that by the power that we put in. And then you multiply it by 100%, which is really just multiplying it by, you're changing it into percentage by multiplying by 100, moving it over the decimal over and writing the percentage sign. Because some people say, oh, should you write 100 and the percent? Well, you understand what we mean. We want it expressed as a percentage. Now, we already said the power out was the secondary, so my efficiency is the power in the secondary divided by the power in the primary times 100%. Now, there will be a few examples of these in some of the homework, so you can try those out. You can use for our power in the secondary, you can still use the same equations. We still use voltage in the secondary, current in the secondary for the numerator, and then for the denominator, voltage in the primary, current in the primary. Okay, so you'll be, in this case, it's an efficiency question when you are given all of these four values, and you'll be like, well, what is there to calculate? Well, we're trying to say that this value will probably be less. If it's higher, then that's wrong, because you can't get more energy out of the system. So there you want to go back and check that you've entered the correct values. And then the power in, we should provide both of those values so that you can compare. Efficiency is really a comparison of what's gone in compared to what came out. And that's efficiency.